Welcome to Lecture 5 of our Probability Theory course. Today we're going to explore an important and practical topic, the theorem of addition for compatible events. In our previous lecture, we learned how to add probabilities for incompatible events, where the occurrence of one event excludes the other. But what happens when events can occur together? This is where the addition theorem for compatible events comes into play, and it's a concept that appears frequently in real-world applications. When two events are compatible, they can both happen simultaneously, and this overlap must be accounted for in our calculations. The formula we'll learn today, which states that the probability of at least one of two compatible events occurring equals the sum of their individual probabilities minus the probability of their joint occurrence, is one of the most frequently used formulas in all of probability theory. By the end of this lecture, you'll understand when to use this formula, how it relates to incompatible events, and how to apply it to practical problems. We'll also explore some important extensions, including the formula of total probability and Bayes' formulas, which are essential tools for more advanced probability analysis. So let's begin our exploration of addition for compatible events. Before we dive into the theorem, let's make sure we understand what compatible events are. Two events are compatible if the appearance of one of them does not exclude the appearance of another event at the same trial. In other words, compatible events can occur simultaneously. Consider this example. Event A is the appearance of 4 aces when tossing a die, and event B is the appearance of an even number of aces. These events are compatible because it's possible to get both outcomes in the same trial. Now, here's the key question. When events A and B are compatible, and we know the probabilities of each event, as well as the probability of their joint appearance, how can we find the probability of event A plus B, which means at least one of the events A or B will appear? This is a question that comes up constantly in probability problems. We can't simply add the probabilities because that would double count the cases where both events occur together. We need a formula that correctly handles the overlap between compatible events, and that's exactly what the theorem of addition for compatible events provides us with. The theorem of addition for compatible events states that the probability of the appearance of at least one of two compatible events is equal to the sum of the probabilities of these events minus the probability of their joint appearance. We express this mathematically as P of A plus B equals P of A plus P of B minus P of AB. This formula is both elegant and intuitive. When we add P of A and P of B, we count the cases where both events occur twice, once in each sum. Since we only want to count them once for the event at least one occurs, we must subtract the probability of their joint appearance, P of AB, which represents the overlap between the two events. This correction ensures that we don't double count any outcomes. A helpful way to visualize this is using Venn diagrams, where two circles overlap. The total area covered by either circle is the area of the first circle plus the area of the second circle minus the overlapping area, which is exactly what this formula expresses. This formula is fundamental in probability theory and is used in countless applications where we need to calculate the probability of at least one of several compatible events occurring. Now let's examine some important remarks about this formula. First, it's crucial to remember that the events A and B can be either independent or dependent. The formula P of A plus B equals P of A plus P of B minus P of AB works in both cases, but we need to calculate P of AB differently depending on the relationship between the events. For independent events, where the occurrence of one does not affect the other, we know that P of AB equals P of A times P of B. Therefore, for independent events, the formula becomes P of A plus B equals P of A plus P of B minus P of A times P of B. For dependent events, we must use conditional probabilities. The joint probability P of AB equals P of A times the conditional probability of B given A. This versatility is one of the strengths of the addition theorem. It provides a unified framework that works regardless of whether events are independent or dependent, as long as we correctly calculate the joint probability. This makes the formula applicable to a wide range of practical situations, from quality control to risk assessment, where we often need to account for overlapping possibilities. Here's an important special case to remember. If the events A and B are incompatible, meaning they cannot occur simultaneously, then their joint appearance is an impossible event, and consequently, P of AB equals 0. When we substitute this into our formula, we get P of A plus B equals P of A plus P of B. This is exactly the theorem of addition for incompatible events that we learned in the previous lecture. So the formula for compatible events generalizes the formula for incompatible events. This is a beautiful consistency in probability theory. The same framework works for all cases, and incompatible events are simply a special case where the overlap term becomes zero. This observation is important because it shows how the concepts we're learning build on each other. The formula for compatible events is more general and reduces to the formula for incompatible events when the events cannot occur together. Understanding this relationship helps us see the big picture of probability theory and appreciate how its various components fit together seamlessly. Now let's apply this theorem to a practical example. Suppose we have two guns firing at a target, and the probabilities of hitting the target are 0.7 for the first gun and 0.8 for the second gun. We want to find the probability of at least one hit when both guns fire once. First, since the guns fire independently, the events are independent. We need to calculate the probability that both guns hit, which is P of AB, and for independent events, this is simply P of A times P of B, which is 0.7 times 0.8, giving us 0.56. Now we apply the addition theorem for compatible events. P of A plus B equals P of A plus P of B minus P of AB. Substituting our values, we get 0.7 plus 0.8 minus 0.56, which equals 0.94. This means there's a 94% chance that at least one of the two guns will hit the target. Notice that this probability is greater than either individual probability, which makes intuitive sense because with two guns firing, the chance of at least one hit should be higher than with just one gun. Also note that we can't simply add 0.7 and 0.8 because that would give us 1.5, which is impossible since probabilities cannot exceed 1. The subtraction of the overlap term corrects this and gives us a valid probability. There's another valuable approach to solving the same problem as shown in the third remark. For independent events, we can also use the formula that the probability of at least one event occurring equals 1 minus the product of the probabilities of the opposite events. This is often simpler and more intuitive. Let's see how it works in our example. The probability that the first gun misses is 1 minus 0.7, which equals 0.3. The probability that the second gun misses is 1 minus 0.8, which equals 0.2. The probability that both miss is 0.3 times 0.2, which equals 0.06. Therefore, the probability that at least one hits is 1 minus 0.06, which equals 0.94. This gives us the same answer as before, which provides a useful check on our calculations. This alternative formula is often preferred because it directly addresses the question, what's the probability that at least one occurs? By considering the complement, what's the probability that none occur? This approach can be simpler, especially when dealing with more than two events, because the probability that none occur is just the product of the individual probabilities of non-occurrence, assuming independence. Having multiple methods to solve the same problem gives us flexibility and helps us verify our results. Now we're going to extend our understanding with the formula of total probability, which is one of the most powerful tools in probability theory. Consider a situation where an event A can occur only in conjunction with one of several incompatible events, B1, B2, through B subscript n, which form a complete group. In other words, exactly one of these B events must occur, and A can only occur if one of them occurs. We know the probabilities of each B event, and we also know the conditional probabilities of A given each B event. How can we find the overall probability of A? The answer is the formula of total probability. This theorem states that the probability of A is equal to the sum of the products of the probability of each B event and the corresponding conditional probability of A given that B event. This formula essentially averages the conditional probabilities of A weighted by the probabilities of the different scenarios in which A could occur. The formula of total probability is extremely useful in practice because it allows us to calculate the probability of an event when it can occur through multiple different pathways, each with its own probability and conditional relationship to the event of interest. Let's illustrate the formula of total probability with a concrete example. Suppose we have two sets of details. The probability that a detail from the first set is standard is 0.8 and from the second set is 0.9. We randomly select a set and then randomly select a detail from that set. We want to find the probability that the randomly selected detail is standard. Let's denote by A the event that a selected detail is standard. The detail can come from either the first set, which we'll call event B1, or the second set, event B2. Since we randomly select a set, the probability of selecting the first set is 1/2, and the probability of selecting the second set is also 1/2. The conditional probability that a standard detail is selected from the first set is 0.8, and from the second set is 0.9. Applying the formula of total probability, we multiply the probability of each set by its corresponding conditional probability and sum the results. This gives us 0.5 times 0.8 plus 0.5 times 0.9, which equals 0.85. So there's an 85% chance that a randomly selected detail from a randomly selected set will be standard. This example shows how the formula of total probability combines information about different scenarios to give us an overall probability, even when we're uncertain about which scenario will occur. The formula of total probability leads naturally to an even more powerful concept: Bayes' formulas. When we use the formula of total probability, we're calculating the unconditional probability of event A before knowing which B event occurred. But what if we conduct a trial and observe that A has occurred? We can then ask, given that A occurred, what's the probability that each particular B event was the one that led to it? This is exactly what Bayes' formulas allow us to calculate. In this context, the events B1, B2 through B subscript n are called hypotheses because they represent different possible scenarios or causes that could lead to A. Bayes' formulas tell us how to update our beliefs about these hypotheses after observing event A. The formula for the conditional probability of hypothesis B subscript I given that A has occurred is the probability of B subscript A times the conditional probability of A given B subscript I divided by the total probability of A. This denominator is exactly the formula of total probability. Bayes' formulas are incredibly important because they provide a systematic way to revise probabilities in light of new evidence, which is the foundation of Bayesian statistics and many applications in science, medicine, and machine learning. Let's apply Bayes' formula to a practical example. Details produced by a factory shop are given for checking to one of two controllers. The probability that a detail is given to the first controller is 0.6 and to the second controller is 0.4. The probability that a suitable detail is correctly recognized as standard by the first controller is 0.94 and by the second controller is 0.98. A randomly chosen suitable detail has been recognized as standard. We need to find the probability that this detail was checked by the first controller. This is a perfect application of Bayes' formula. We have two hypotheses: B1, that the detail was checked by the first controller, and B2, that it was checked by the second controller. The event A is that a suitable detail is recognized as standard. We know the prior probabilities of the hypotheses, 0.6 and 0.4, and the likelihoods, the conditional probabilities of A given each hypothesis, 0.94 and 0.98. Applying Bayes' formula, we calculate the probability that the detail was checked by the first controller given that it was recognized as standard. This equals 0.6 times 0.94 divided by the sum of 0.6 times 0.94 and 0.4 times 0.98, which approximately equals 0.59. So even though the first controller is less accurate, the probability is about 59% because it's more likely that the detail was given to the first controller in the first place. This example beautifully illustrates how Bayes' formula combines prior probabilities and likelihoods to produce updated posterior probabilities.